Hello, everyone, from a rather dreary Melbourne. So welcome to this Austmine webinar. I'm Grant Philpotts. I'm the Membership Manager, and I'm pleased to be your host for this webinar today. Before we begin, I'd like to acknowledge that I'm hosting this webinar from the lands of the Burrarung Bund Warren and Wurundjeri Woi Wurrung peoples of the Eastern Kulin Nation, and also pay respect to their elders past, present and emerging. I also acknowledge the traditional custodians of the various lands on which you all work today and the Aboriginal and Torres Strait Islander people who are attending this webinar. Next slide, please. Today's webinar is the second Environmental Tech Talk of our ESG webinar series, which is running across the year. In previous webinars, we've explored the key trends, challenges and opportunities emerging from the mining industry and met sector as the global focus on sustainability and ESG issues intensifies. You can view all recordings and register for webinars through our website, and you can see the upcoming webinars that we've got going on at the moment as well. For this webinar today, we have 4 fantastic tech talks focusing on conserving water resources in mining from OLEOLOGY, AECOM, oil utilities, and clean tech water. These tech talks will delve into the technologies and processes that are reducing water consumption in mining and negating challenges surrounding water quality and impacts on biodiversity. Our speakers today will present solutions encompassing areas such as recovering water from tailings, water treatment, and monitoring and compliance. The tech talks today are pre-recorded, but we have each of the speakers online for our live audience Q&A, which will take place after the session. You can use the Q&A button at the bottom of your screen to send through questions at any time. You can also upvote on other audience questions that you may want answered. So without further ado, I'd like to move on to the first presentation from Paul Callaghan, Director of OLEOLOGY on water resource and treatment. Thank you, Paul.
Paul Callaghan from OLEOLOGY, talking today on water on mine sites, the resource, that is the treatment and reuse of it, and how we can go about doing that. The words most commonly addressed as part of the community regulators and public expectations are reduced, reuse and decarbonise. It's very black and white and stark. It's a constant consideration for any resource operation. Environmental resources are limited, particularly the fresh water. Mine water consumption represents approximately 4% of national water demand, and that's growing with mining production and the number of mines that are opening. Mining in some areas at a local level places demand on water, which is a limited or scarce resource in that locality. Environmental waste and the concentration of contaminants in discharge, their impact on the environment are increasingly scrutinised, with regulators reducing contaminant concentrations allowed in those discharges. That is only going to get worse with time. Some mining water uses that we'll have a look at today, and we'll concentrate only on a couple of those, are the camp ore production, heavy and light vehicle washing, and waters out of the MEM. Each of those areas of water application in the mine brings a different range of contaminants that require separate treatment. Ideally, each of these waste streams is treated separately. Mixing creates a more complex waste, requiring an extended treatment system with greater complexity, increasing costs, increasing wastes, and increasing maintenance. So some mining water sources, generally for the camp, it's fresh water, most likely through the use of an RO to bring water quality up to scratch. Ore production and tailings generally requires RO water, and again, heavy and light vehicle washing, water around the MEM is also RO type water. The water quality for most of these uses requires treatment via the RO or reverse osmosis for the reduction of salinity, mineral salts, hardness. Reverse osmosis plants are energy and capital intensive and generally can form a restriction on the availability of water to conduct some of those operations around the mine site. Use of RO water also comes at a cost when you consider the ESG implications, both the carbon footprint and increases operational and production costs as the RO ages or its increase in capacity is required. From looking at these sources for use, mining water footprint and carbon footprint can be established, or thus a measure thereof. So a determination can be made on improvements. Resource is a model to reduce mining water footprint, depending upon the technology employed, and also to reduce the carbon footprint, the waste reduction and mitigation of operational cost and risk. These are important factors to consider in the total of looking at the mining resource of water. Mining, when considering the water quality for most of these uses, requires the treatment by RO, the reuse of treated water as an ESG resource brings about significant benefits. The resources that we can look at today are around camps, for instance. The sewage or wastewater treatment systems often are at a limit and require additional treatment in order to raise the capacity of the wastewater treatment system. And in general, they're limited by the amount of nutrients contained within that water system on discharge. We now have technologies which enable very simply for those improvements to be undertaken. Ore production, tailings, heavy metals is the major issue associated with that. Heavy and light vehicle washing, the range of oil and greases, suspended solids, PFAS, and glycol. In fact, the PFAS is appearing and we're receiving more inquiries for treatment of PFAS across mining operations, both current treatment of water and also groundwater. So it pays now to consider PFAS removal in areas where it is likely to appear before it actually gets out from water treatment systems and discharged to groundwater. Mining water resource, for the camp, retrofits for increased nutrient removal and PFAS filtering, making water quality suitable for reuse in various applications around the mine. Heavy and light vehicle and the MEM workshop, full recycle of water for washing, the water quality being maintained at Department of Health standards, and compared to reverse osmosis operating cost, there's a significant reduction in both the production cost and also it reduces the draw on local resources. Additional to that, we also have reductions in wastes. So a little bit further to that, if we then consider ore productions and tailings is now significant. When we consider ore production and tailings, there are now new innovative technologies for reductions of heavy metals depending upon the types of tailings and the concentration of metals that are in those wastewaters that are now suitable for implementations at site. Just to concentrate on two of those resource opportunities, the camp, the retrofit of a modular plant for increased nutrient removal and water quality, including PFAS removal, are also available as part of the filtering systems that we offer. Heavy and light vehicle washing with the fully modular plants capable of full recycling of water, reducing the OPEX as compared to reverse osmosis, plus reduces the water waste streams associated with reverse osmosis permeate, further improving the environmental footprint and also lowering the energy, carbon footprint, and associated operating costs with that. Overall, the OLEOLOGY operation has wastewater treatment plants that are a staged sequence. The robust sequence of treatment enables improved removal with reduced size, because these systems are very modular, they're able to be removed from one side to another, giving rise to large costing reductions and savings, waste reductions as well, where in isolated locations that becomes a significant consideration, and importantly, the mitigation of risk. The more availability of water because of resourcing in the method by which we reuse water reduces risk for both discharge and also availability of water to continue mining operations, or in fact increasing mining operations without further draw on local water resources. Thank you for your time.
Fantastic. Thanks for that, Paul. If you have any questions for Paul, please use the Q&A button that you'll find on the bottom of your screen to submit those. So our next presentation is by Ali Nadaran, Technical Director, Geotechnical and Tailings, AECOM, on recovering water from mining tailings. Thank you, Ali.
Good afternoon, everyone. My name is Ali Reza Naderian. I'm a Technical Director in the Ground Engineering and Tailings Group of AECOM in Brisbane. Before I start, I'd like to thank Austmine for organizing the Tech Talk series and for giving AECOM the opportunity to participate. Today, I'll be talking about a case study for a recent tailings project that we did for a large mining company in North Queensland. As you'd appreciate, supplying water to mining operations in Australia and in particular in Queensland is quite costly because of the remoteness and the dry areas where they're located. Water is used for different mining activities, but the mineral processing plant is where most of the water is used. And that water is usually sent eventually to a tailings dam where it's stored permanently, or some of that is recovered and some is left to evaporate and wasted. So the operation of a conventional tailings dam can be quite costly because of the capital cost of construction of the dam. The water that's actually left to evaporate is quite costly, and it can cause environmental impacts, and water can be the cause of a dam failure, which could be fatal. So mining companies are looking always at different solutions for eliminating the need for a tailings dam. With the conventional tailings deposition, which is estimated to be used in 90% of Australian mines, the tailings slurry is actually sent to the tailings dam at about 20 to 30% solid content, which means it's got about 70 to 80% of water by weight in the slurry. And that water is quite costly because it's the water that has been often purchased to be used for the mining operations. And apart from that, there is a cost involved with the transport of that. There is a cost involved with supplying or purchasing land for construction of the tailings dam, the construction cost, and water management and potential remediation works. Not to mention the closure of tailings mines are quite costly. There are alternative technologies that have emerged recently that are used by several mines to thicken the tailings before it's actually sent to the tailings dam. This is actually extracting water from the tailings slurry and therefore making use of the water that's extracted from the tailings for other operations or for recycling to the mineral processing plant. These technologies involve thickening the tailings, includes paste and also filtered tailings, but they come at a very high cost, not just the capital cost, also the operational cost, and as such, they've not really been really popular with the mining companies, and not many mines are actually using them. With that in mind, we were approached by a mining company in North Queensland to provide them with an alternative solution for their tailings disposal. This mine is currently operating 3 conventional tailings storage facilities, but they wanted to actually use alternative solutions to save on the water that has been actually wasted in their tailings dams, and also give them the opportunity to eliminate the need for the tailings dam altogether, and in the process eliminate the risks involved in maintaining a tailings dam. So they asked us to look at alternative solutions that can give them the opportunity to close their tailings facilities and meet the strict regulatory obligations that have been imposed on mining companies after introduction of the global standards for tailings dams. The solution that we offered for this operation was not requiring any changes to the processing plant, so the tailings was still actually sent to the disposal area in the form of a slurry, similar to what they have been doing with the conventional tailings facilities. However, the tailings was actually placed in a number of different smaller storage areas, which we call tailings cells, which allowed the operators to combine that with flocculants, which was added at the time of deposition to extract the water, and also gave them the opportunity to actually have the tailings consolidated in the cells for a few weeks before they come back and actually take the tailings out. At the time of completion, the tailings was almost semi-dried, not quite dried, but it was actually dry enough to be loaded on trucks and taken to the waste truck dumps, and then stored there safely and capped, so there are no environmental consequences for that. This has actually saved them a lot of money with saving on water, and also allowed them to use the water that was extracted in the CHPP, the coal processing plant, and it was actually gave them the opportunity to eliminate the need for a tailings dam altogether. Here I have shown a sketch that shows the design we did for this mining operation. As you can see, rather than having a big tailings dam, we have designed this operation to have several smaller tailings cells, each of them actually taking about 1 week of tailings production in them, and therefore allowing the rotation of the deposition into a number of cells before we come back to the first one and extracting the dried material from that, making it ready for the next deposition cycle. As I said, it's actually designed to have about 1 week of tailings in one of these. We add the flocculants and extract the water from that at the time of deposition, and we leave it for 2 to 3 weeks before we come back to it and actually excavate the dry tailings from it. In this table, I have tried to show you the volume of water that was actually expected to be extracted as part of this solution. As you can see, the tailings is placed into the cells at 25% solid content, and for a mine that's actually producing about 1.04 million tons annually, that means per week we are actually putting about 80,000 tons of tailings into each cell. Out of that, it's estimated that about 60,000 cubic meters of water is actually placed in the cell at the time of placement. But after 7 days of deposition, adding the flocculants, we were actually extracting about 40,000 cubic meters of water from each cell. And after the drying period, which we allowed about 2 weeks for consolidation under the weight of the tailings, that increased to about 46,600 cubic meters of water that was extracted. The water was sent to a temporary sump, from where it was actually directed back to the coal processing plant, and we estimated that at that production, we will be saving about 2.4 million cubic meters of water annually, which at around $3,000 per megaliter, this will amount to around $7.2 million per year, only on the cost of water. Now, this does not actually include the cost of construction and maintenance of a tailings dam, which is significant by itself. So to wrap up here, the proposed alternative solution that we offer for this mine conserves a large volume of water and therefore reduces the operational cost. It minimizes the potential for environmental impacts from tailings dam, eliminates the need for a tailings dam altogether, and therefore reducing the cost for operation. And most of all, it's actually meeting the regulatory guidelines and allows the mine to progressively close the tailings dams and go to closure and rehabilitation. Thank you, everyone, and I'm happy to answer any questions if there are any.
Great, thanks for that, Ali. Next up is Vince Asagi, Head of Mining Isle Utilities, with a presentation on taking a holistic view to water management mining. Thanks, Vince.
Hello, and thank you to all of my Austmine members and guests. The title of my presentation is A Holistic Approach to Mine Waters, and in holistic we mean the whole mining cycle from exploration through to closure. I'd like to share with you a little bit about Isle, how we rethink how organisations can approach this issue. Before I do that, I'd like to welcome to country and basically pay our respects to the Wurundjeri elders, past, present and emerging, for the land that I'm presenting to you this from. So Isle is an innovation and collaboration business, and its DNA is in that space around water. We have expertise globally with over 100 employees, and that's growing. But more importantly, or not more importantly, more interestingly, we have working relationships with over 250 universities, 100 research organisations, 50 incubators, and over 7,000 technology providers, of which many of those technologies have been presented to our clients, of which another factor has been implemented. We work with municipal water, we work with government, we work with industrial players, and we work with mining companies. And that experience, along with all of that research backing, gives us a lot of knowledge to bring outside industry thinking into industries such as mining. We're unbiased and independent. We don't represent any technology company. We're interested in finding solutions that meet our clients' needs, and our expertise is looking across horizons to do that. It's an interesting fact about where mining is going, and that is that 50% of the world's largest mines will close within the next 20 years. And this is going to put pressure on the demand side and supply side for things such as water, but it's water management, but it's also the overall commodity balance. We're going to need more commodities coming on stream, so that's going to mean more exploration. It's going to need more mine extensions and so on. So all of these things are going to present new challenges to mining companies to meet future challenges. In doing that, you really need to take a long-term view and a strategic view to scanning what might help you manage that complex future. One of the ways we do that with Isle is we run some design thinking workshops, but then ultimately look at technology scanning over horizon. The TRL levels you're seeing here were developed by NASA in the 1970s to basically identify how mature a technology was. So obviously at level 1, we're just starting to thinking, and at level 9, it's in the market. You know, what we've realised is that most of our clients are worrying about what's in the market now, because they have pressing issues, whether it be shareholders, bosses, etc. And what we have the ability to do, because of how we're organised, is to take the pressure off the mining companies and look for alternatives for them that might span a different horizon. And that's work that we've been doing with mining companies, with industrial companies, and with municipal water companies. So let's just quickly have a look at a couple of those examples. First one is a water authority. They were running out of water and they needed to find another source and or conserve water. So a couple of they looked at projects to do that, things like, shower heads and water catchment at houses and those sorts of things, standard low-hanging fruit. But we managed to look into, I guess, a more broader array of technologies, and we looked at evaporation in dams. We looked at seepage from dams. We looked at the technologies to assess the quality of the dam walls, whether they were stable, whether they could hold more water, etc. We also looked at pipe mechanical integrity and leakage analysis from their infrastructure. And we also looked into things like desalination, which is a proven technology, but how do we power it so that we don't add to the carbon challenge? So all of that was boiled down into a few projects that they could look at going forward, do some cost benefit analysis, more community engagement. And, that project has been very successful and has now been, if you like, replicated with a New South Wales government department. So, this sort of outside knowledge that may not seem as relevant to mining, we see as potentially adjacent to mining challenges. The next and final example is one of a large global miner that had a mine closing in 15 years, or planned to close, as those know it. What's planned isn't always what happens. And originally the plan was to treat the wastewater with lime, or the mining food waters with lime. When that was studied, it was identified that it was commercially and logistically impractical, and we were asked to look at various new technologies to solve that problem or to deal with that challenge. What we're able to do again is to step back, look across the horizon, and identify technologies that were emerging. And as you can see in the slide, there's different numbers of ideas that we threw up at different technology readiness levels. And through a process that we run over a period of time, we were able to boil those down to 3 significant technology innovations that the mining company was happy to progress to further on-site trials. That's still in progress, and that work has then resulted in further work with that particular miner, looking at similar technologies, but targeting valorisation of minerals out of the MIW. So you can see that there's a proven record here. Short presentation. Thank you for your attention. Hopefully you found some of it interesting and it's piqued your curiosity. If so, please contact me on the numbers on the screen. And if I'm not able to help you, I'll certainly get somebody else to do so. Thank you and good day.
Thanks, Vin. That was great. If you've got any questions for Vince, please use the Q&A button at the bottom of your screen. Now on to our final presentation from Sivan Ishran, Business Development Manager, Clean Tech Water, who is looking after their water treatment solution at the Fosterville mine. Sivan?
Hello everyone, my name is Sivan Ishran. I'm the Business Development Manager for Clean Tech Water. It's a privilege for me to be here talking to you at the second in the series of Austmine's ESG Tech Talks. This particular one is looking at water management solutions. I want to tell you about our DESALX technology, which is very suitable for sulfates, hardness, and acid mine drainage in mine water applications. As we know, mine waters have some unique challenges. They have sulfates, they have iron, they have manganese, calcium, and magnesium. Most of these things are a problem for membranes that lead to scaling. As a result, we end up with evaporation ponds because of the lower recoveries that are achieved through membrane systems. These ponds can become very unsightly, or depending where you are, if you've got bushfires, they could be subject to damage from that or sabotage. On top of all of that, they're very expensive to decommission. First, a little bit about Cleantech Water. We're an Australian company that's publicly listed on the Australian Stock Exchange. Our ion exchange technology is suitable for water treatment and metal recovery. We're also developing our own geomembranes, and you can find that at our pneumatic website. Our head office is in Melbourne, together with our research facilities. We're an office in Africa and also in Beijing. We work with a number of partners in the Middle East and in South America. We've done a number of projects across the globe, including some pilots for acid mine drainage sulfates in South America. We have a number of technologies in our portfolio that is very suitable for mine water applications. Today, I'll be focusing on our DESALX technology, which is a membrane-free desalination process that is suited for sulfate removal, hardness, and acid mine drainage. Our HYROX technology and CIF technology can sometimes be used in those applications, but they're also very suitable to different mine water applications. At the core is our continuous ionic filtration technology. What happens here is we move the resin around in a number of ion exchange columns. The feed water comes in from the bottom and moves in a countercurrent fashion to the resin, which is introduced at the top. This all happens during absorption. Once the contaminants we want to remove are loaded onto the resin, we then move the resin into a wash column and it's given a rinse. Any suspended solids that might come in the feed are also removed in this stage before the clean loaded resin is moved across into the desorption column. In the desorption column, we use chemicals to regenerate the resin. We can use cheaper chemicals such as lime and sulfuric acid that provide a lower operating cost because our ion exchange technology can tolerate some solids formation. We then rinse the resin and send it back to be reused back in the absorption process. In DESALX, which is our membrane-free desalination process, we go through a two-stage ion exchange process. In the first stage, the feed water is introduced from the bottom, where the cations, the divalents and the trivalents are removed. We then move the water across into the second stage, where the anions, such as the sulfates, are removed. The Fosterville gold mine in Victoria is where we installed our first DESALX plant. The feed water contains some arsenic and antimony, as well as hardness from calcium and magnesium, coupled with some sulfates there. The client's thinking at the time was to go for a UFRO. When we saw this, we thought it was a very good fit with our DESALX technology. It provided the opportunity for a higher recovery. We were close to be able to support from our Melbourne office to be able to support the operations, and it would reduce the company's overall dependence on mains water coming in as well. There were some risks. It was new, moving bed ion exchange technology is new, and they would be the first water treatment plant project in Australia. The flow sheet we had in mind started with an arsenic antimony precipitation process using ferric chloride. Once that had been removed, the water would move off into our DESALX unit, where we would remove the calcium and the sulfate using ion exchange, and we would use sulfuric acid and lime to regenerate the resin. That combination gives us a reusable gypsum-based brine for disposal. The permeate would then go on to an RO, where it's cleaned up for reuse in the processed water circuits. This reduced the dependence of the mine on make-up water coming from the town system. The layout of the plant would start with the feed water coming into the clarifiers and then moving across into the ion exchange system here, where you can see the stage 1 cation absorption columns, followed by the stage 2 anion absorption columns. These columns are typically 3 to 3.5 meters in diameter and up to 10-12 meters tall. So they're very good for fitting into small spaces where you've got footprint constraints as well. We chose this process because, as you can see, the TDS in the feed water is made up of calcium, magnesium, and sulfates. The sodium content was very low. So to quickly summarize, the 2 megalitres a day DESALX plant we put in at the gold mine in Victoria took us 2 years to construct at a cost of $3.5 million to the client. So on the way, we learned a couple of important lessons that we've taken away with us. First of all, in terms of the hydraulics in these larger scale columns, we got a better understanding of the resin movement in those. By working with the suppliers for screens, we optimized the design and operation of those screens for future projects. With the pre-treatment for the arsenic and antimony precipitation, we found that by seeding and recycling the sludge, we were able to reduce the size of the footprint and the maintenance on that part of the process. And the importance of having a larger buffer capacity between our DESALX plant and the RO, mainly because the RO has more frequent stops that the Ionic change plant doesn't always need. So to summarize, the DESALX membrane-free desalination process provides a ZLD solution without any saline brines. We can take mine waters, we can take oil and gas waters, we can take groundwaters that are low in sodium and convert that into processed water, irrigation water, or drinking water as the need requires.
Wonderful. Thanks for that, Sivan. Now it's time for some Q&A. I'd like to welcome our speakers back for the questions. They're all on board now, so please use the Q&A button at the bottom to send through any questions you'd like answered. We've got a number in there at the moment. Now, we are on track to get finished by 1:15 Melbourne time, so I'd ask everyone just to be conscious of that as well. So the first question comes from Simone Flynn. How does the system measure oil and hydrocarbon removal? How is the performance monitored? Analysts?
Certainly, we can provide some assistance on that. Oil content monitoring is something that we're very familiar with. We do a lot of work in the oil industry, as well as mining and general industry. Oil industry is heavily regulated. So for oil and gas analysis, there's a range of equipment which is used traditionally, most of which utilize standard methods which are calibrated at site relative to the oil and gas or the oil composition, the TRH ranges. For more complex installations where hydrocarbons will be of a solvent nature, there are equipment that is now available which come at a higher cost, which use microscopy, which is able to detect BTEX and so forth in water as well. Does that help with the answering of the question?
Certainly does, Paul. Thanks for that. So the next question is to Ellie. What was the consumption of the secondary flock per tonne of dry tailings recovered, and what was the cost per tonne?
Yeah, this actually depends on the nature of tailings, but for this particular example that I provided, it's very small, it's less than 1%. In fact, we had a 40 cubic meters or 2 of 20 cubic meters tanks on site and a delivery of 20 cubic meters per month scheduled for this or envisaged for this operation. So you can work out from the volume of tailings that we put in the cells per month that it would be a very small number. In terms of the cost, I have no idea at this point in time. I can work out and get back to you on that, but it wasn't really a significant cost compared to the cost of maintaining a tailings dam. So it was quite effective and efficient.
Excellent. Thank you, Ellie. So another question, are most mines suited to dry tailings disposal, and what has been the limitation to widespread industrial use? Anyone? That's open to anyone to answer.
Again, yes, it can be used, but the limitation is the grading of the tailings. You need to make sure that you can actually apply the flocculants efficiently and get the most of the moisture out of the system before you actually deposit or dispose the semi-dry tailings into the waste rock dumps. So it really depends on the nature of tailings, but it can be applied to most tailings, I suppose, except for the ones that are really fine-grained, and it's difficult to actually get the moisture out of the system with those tailings.
Ali, you're proving to be quite popular. So, Ali, does the ground sieve or sales result in any contaminated groundwater, or is this part of the monitoring process and similar to a tailings dam?
Well, obviously, for any waste rock, you will have the monitoring process implemented for all waste rock dumps. But with this, you make sure that you will actually have a certain compaction below where the tailings is placed, and you also make sure that you progressively cap them as you place them in the waste rock dump. So moisture is not actually penetrated into the cells, into the sieves, and therefore the chance of actually getting groundwater contamination, given that most waste rock dumps have a liner placed under them, it's actually quite small. In fact, compared to a conventional tailings dam, it would be much a smaller chance of or risk of groundwater contamination.
All right, Ali, what about the stability of the cake, given it's around 40% moisture?
Yeah, I didn't get the question here. If the stability is referring to when it's actually placed in the waste rock dump, it is actually a small cells compared to the whole, if you like, size of the waste rock dump, and it's actually placed in between the waste rock, and it's actually capped. So no, it won't be a problem with the stability, but for sure it can actually, because if you consider the fact that the tailings would probably be a small portion of the waste rock dump, it's not going to be a stability problem. But for sure it can be designed. If there is a concern, it would be designed to make sure that it won't cause any stability issues.
Okay, Ali, can you elaborate on what and how you add to the tailings in the cells to extract the water?
Yeah, here we're adding flocculants to the tailings slurry as it's actually placed in the cells. And I didn't actually go into details of that because of the time limitations, but there has been actually a comprehensive study on the tailings that's actually placed into them beforehand, and the rate of flocculant and the type of flocculant. So before we even get to the design for the cells, we have done actually maybe a year or more of a study on the nature of the tailings, the current tailings and the future tailings also, to make sure that the flocculants are actually efficient and they work on this particular type of tailings. And then it's actually added at the same time as it's deposited into the cells, just at the on site where the cells are. We have a pipe that comes in with the flocculants and it's added to the slurry. And we were envisaging that we get most of the water out within 1 week. As you saw in the table, we had tailings solid content increasing from 25 to 50% within 1 week.
Ali, what is tailings production rate that was dewatered in the tailings cells with flocculants?
Yeah, again, that was shown in the table. That was only an example table for a 1 million ton of tailings production, solid tailings production. It was about 80,000 cubic meters of 80,000 tons of tailings per week in each cell.
Excellent. Now, Sivan, we've got a question for you there. What happens to the antimony and arsenic waste brine removed from the water prior to RO processing? Can the materials be reclaimed?
Yeah, antimony is obviously valuable, but I don't believe in this particular case there was sufficient there to be able to recover it. We have a very similar plant and an antimony roaster in Oman, and there's probably a little bit more antimony that comes out of that one that is probably recovered there. In terms of metal recovery, you can use ion exchange to selectively remove precious metals and recover those ahead of the water treatment. So we've looked at a number of applications where we can extract copper out of mine water, for example, to help pay for the water treatment plant.
Excellent. So, Ali, again, what was the quality of the water from the tailings drying? Did it need further treatment? Could it be reused?
No, it was actually sent directly to the coal processing plant. If there was any issues with the quality, they could probably be mixed with the water that we had from other resources.
Excellent. We've just got a comment lastly of all. So at Ali, carbon footprint of trucks and cost dredging the soils is not cheap.
Absolutely, but you have to actually do a trade-off study for that. For sure, if you're looking at alternative solutions like, I don't know, paste or filtering, the carbon footprint for those will not be cheap either because it uses a lot of energy. But the reality is you have to put all the pros and cons in one basket and have a look and see which one is actually more efficient. And I agree with you that the carbon footprint for trucks is not cheap, but the saving that we get from this probably is enough to overcome that.
All right. Well, thank you very much for that. So I'm afraid that's all the questions, the time we've got for questions at this time. I'd like to give a big thanks to Paul, Ali, Vince, and Savan for their time and insights today. It's very valuable. Before we go, I'd like to draw your attention to the next Environmental Tech Talk in our ESG series on managing waste and creating value. You can book for that through the Austmine website right now. Thank you to everyone who's attended, and we look forward to welcoming you to the next Austmine webinar. And everyone have a great day and stay safe. Thank you very much.
Thank you.